Hey everyone, today we're going to talk about memory, how it works, and more importantly, how we can make it work better for us. We're going to dive into a really powerful science-backed technique that can honestly change the way you learn just about anything.
But first, let's start with a question I think we've all asked ourselves, probably the night before a big test or when you bump into someone and their name is just gone. Why is it that we forget things so fast? You feel like you've learned it one day and poof, it's vanished the next. It's super frustrating, right? Well, it turns out science has a pretty good explanation for this.
All right, so here's our game plan for today. We're going to cover 4 big ideas. We'll start with the problem itself, something called the forgetting curve. Then we'll look at the first real attempts to solve it using algorithms. After that, we'll get into the why, the actual model of memory that makes this all tick. And finally, we'll peek into the future and see where this tech is headed.
Okay, first up, let's talk about the fundamental challenge that really every single one of us faces when we try to learn something new.
So this is it, the forgetting curve. And what it shows is kind of wild. When you learn something new, your memory of it doesn't just fade away nice and gently. Nope, it drops like a rock, especially right at the beginning. That first super steep drop, that's our biggest enemy when it comes to learning. So how do you fight back against this? Well, the solution is surprisingly simple. You just review the information. Every time you successfully remember something, you hit pause on that forgetting process. And here's the amazing part. You don't just reset the clock. You actually make the curve flatter. Each review makes you forget that thing more slowly in the future. Pretty cool, right? Now the real magic is in when you do those reviews. The trick is to space them out. For brand new stuff, the things that are still kind of shaky in your brain, you need shorter gaps between reviews. But as you get more comfortable with it, you can wait longer and longer and longer. This idea, this strategic timing, that is the absolute core of spaced repetition. Okay, so this whole sounds great in theory, but it brings up a huge practical problem. I mean, it's one thing to do this for a few dozen flashcards, but what if you're trying to learn a language with thousands of new words, or study for a medical exam with just an ocean of facts? Manually tracking a different forgetting curve for every single item and figuring out the perfect time to review each one, it's impossible. And that's exactly where computers come into play. And this brings us to our second section. Because the solution didn't come from a big corporate lab. It came from a student who was dealing with this exact overwhelming problem. So I want you to meet Piotr Wozniak. It's 1985. He's a college student trying to learn a bunch of English and Polish vocabulary, almost 3,000 different things. And he was totally losing the battle. He was a meticulous note-taker, and he realized he was forgetting over 40% of what he was studying. For him, that just wasn't good enough. He knew there had to be a better way. So what did he do? He basically started doing experiments on himself. His goal was to find the longest possible time he could wait between reviews while still remembering almost everything. He wanted a forgetting rate below 5%. This table here shows some of his data for the third time he reviewed a set of facts. You can see he's testing different intervals, and based on this, he figured out that around 16 days was the sweet spot for this stage. He was literally reverse engineering his own memory. Through all these painstaking experiments, he actually created his first algorithm on paper in 1985. He called it SM-0 for Super Memo 0. Then, once he got his hands on his first computer, he started simulating and tweaking his model, which led him, in 1987, to create the legendary SM-2 algorithm. So what made SM-2 such a game changer? Why is it still the foundation for so many learning apps today? Well, it came down to 3 big ideas. First, you break down everything you want to learn into tiny little question and answer pairs. Second, you schedule reviews with those intervals that get longer and longer over time. And third, and this was the real genius move, it used something called an ease factor. After you'd try to remember something, you'd grade yourself on how easy it was, and the algorithm would use that feedback to customize the schedule just for that one fact. So these early algorithms were built on what worked in practice. But to make them even better, you really need to understand the theory behind it all. So let's move on to the why. Why does this stuff actually work? Modern theories of memory tell us that just saying a memory is strong or weak is too simple. It's better to think about 2 different things. First, there's retrievability. That's basically, can you remember it right now? It's about your immediate performance. Then there's stability, and that's about the long haul. How durable is that memory? How long will it stick around before it fades? But wait, there's a third piece to this puzzle. We all know this intuitively, right? Learning the Spanish word for apple, manzana, is way easier than learning the word for, I don't know, jurisprudence. That's the third variable, difficulty. Some ideas are just naturally harder to get to stick in your brain. And so there you have it, the whole picture. To really model how memory works, you need to track all three of these things: retrievability, stability, and difficulty.
Now, get ready for this, because this is probably the most fascinating, kind of counterintuitive part of the whole thing. When is a review the most powerful for building long-term memory? It's not when the info is fresh in your mind. It's when you review it right on the very edge of forgetting it, when you have to struggle a little bit, when that retrievability is low, but you still manage to pull out the answer. That's what creates the biggest jump in memory stability. That little bit of a struggle is what makes the memory stronger.
Okay, this all brings us to our final section. Now that we have this really powerful three-part model of memory, how have things changed? How have we moved beyond those early fixed rules of SM-2? Well, modern algorithms are absolute data sponges. They're not just looking at your simple good or bad rating, they are tracking everything: who you are, what you're learning, exactly when you review it, how long it's been since the last time, your exact response, and even how many milliseconds you spent thinking before you answered. And here is the huge leap forward. Instead of just following a one-size-fits-all rulebook, these systems use all that data to build a predictive model of your specific, unique memory. It learns how you forget and how you learn for every single item you're trying to master. The ultimate goal of these super advanced algorithms can really be boiled down to 3 steps. First, they use that 3-component model to figure out the current state of any given memory. Then, they calculate the cost, like how much time and effort it would take to relearn something if you forget it. And finally, they solve for the optimal path forward, the most efficient schedule of reviews to get that memory locked in for the long term. So, what's the big takeaway from all this? We've gone from figuring out review schedules with pen and paper to algorithms that create these dynamic, hyper-personalized learning plans. They're designed to find the absolute shortest, most efficient path for you to build real, durable, long-term knowledge.
You know, this whole field is just this amazing mix of brain science, data science, and computer science. And like Jarrett Ye, who wrote the material we've been exploring, says, the journey to fully understand and optimize our own memories, well, it's still happening. It's a mystery that we're all invited to help solve.